ITC Lunch. It looks like a full house today, and we can guess why. BICEP 2, Keck, and Planck are in the titles of the first two talks. But we also had an excellent ITC colloquium by Tesla Jeltema, and she will speak a little later on another topic. If I had to summarize your colloquium, I would say that the dark matter is still dark as far as we know. And so the first talk would be by Cora Dvorkin, and she will speak, as you can see, about the joint analysis of BICEP 2, Keck, and the Planck data. And then that will be followed by John Kovac, who will tell us about B modes and the ongoing BICEP Keck program. In fact, I just read an article in Nature talking about those future programs and saying that BICEP is well ahead of the competition. That was a statement that
that was attributed to John.
No, someone related. And then we have a visitor that is giving the CFA colloquium from Space Telescope Science Institute, Jason Kalirai, and he will tell us here about Astronomy 2020 science capabilities with the JWST and WFIRST Flagships. These are two major missions, and he will keep everything within 10 minutes. And then we'll hear from Tesla again, and she's visiting us from UC Santa Cruz. She will tell us about early results from the dark energy survey. Cora.
Hello.
So hi, I'm Cora Dvorkin. I'm a Hubble and ITC fellow here at the CFA. And today I will talk about the results of a joint collaboration between the BICEP 2 Keck team and the Planck team that I had the pleasure to join when I came here in the fall of last year. The results of this analysis were submitted to the archive last week. Okay, so here's where we stand in cosmology today. We have a standard model of cosmology that we know as lambda CDM. We have a homogeneous background, and we measure the parameters of this background quite well. We have learned that we have approximately 5% of baryonic matter, 27% of cold dark matter, approximately 68% of dark energy. On top of that, we have perturbations, and we measure the parameters of these perturbations quite well. We know that they are nearly scale invariant and approximately Gaussian. Now, in March of last year, the BICEP 2 collaboration released the detection of angular scale degree B modes in the sky. In the fall of last year, the Planck collaboration also measured the polarized dust emission in our galaxy, finding that it had a higher amplitude than was initially expected. So we as a community remain with the question, do we need to extend our standard model of cosmology? Are there primordial gravitational waves? Was the signal all dust? Was it all gravitational waves? Was it a mix of these? So let me stop for a second and give you a brief review of CMB polarization. The CMB is linearly polarized. Polarization is generated by Thomson scattering of photons of free electrons. So it's the local temperature quadrupole that each electron sees along the line of sight that sources CMB polarization. The CMB polarization can be decomposed into E modes and B modes. The E modes and B modes are the tensor analogs of the curl-free and divergence-free component of a vector field. The E modes have their direction tangential around hot spots and radial around cold spots, and the B modes are rotated by 45 degrees. So scalar sources, such as density fluctuations plus linear evolution, generate E modes, and gravitational waves, which distort space-time and create a CMB quadrupole, or nonlinear evolution, such as, for example, gravitational lensing, generate B modes. So in the next few slides, I will talk about the three experiments that were involved in this joint collaboration. I'm showing you here the BICEP 2 experiment that has one receiver. It measured, it took 3 years of data from 2008 to 2010. It took data at 150 gigahertz, and it measured over approximately 400 square degrees in the sky, which is about 1% of the sky. Here I'm showing you the Keck experiment. This experiment has 5 BICEP2 type receivers, and it took data from 2012 to 2013 at 150 gigahertz. It continued taking data at 95 gigahertz. This data was not included in our analysis, and John will discuss this in his talk, I believe. So a combination of these two experiments, BICEP2 and Keck, gave us a final map with depth of 3.4 microkelvin arc minute, which is the deepest map of CMB polarization ever made. Of course, some of the modes are lost due to apodization and filtering of these maps. Now, the Planck satellite is the third space mission that measured the CMB after COVID, which was first, and WMAP. It's an ESA-led mission. It was launched in 2009, and it finished taking data in 2013. And it gave us full sky maps that were producing 7 polarization-sensitive bands centered at 30, 44, 70, 100, 143, 2017, and 353 gigahertz. These are the Planck full sky maps. They measure 9 full sky maps in intensity and 7 in polarization. So here we can, we can see the maps. Galactic synchrotron emission is strongest at lowest frequencies. Galactic dust emission is strongest at high frequencies. And therefore, the CMB remains mostly uncontaminated at mid frequencies and high latitude. Here I'm showing you a comparison between BICEP2 Keck maps on the left and Planck maps at 353 gigahertz on the right. We can see the temperature map and the polarization maps decomposed into Q and U Stokes parameters. We can see that the Planck maps, which are seen as, these maps are as if they were seen by BICEP Keck, so they have been smoothed by the beam profile of BICEP2 and Keck, and also filtered in the same way. We can see that the polarization maps are about 10 times less sensitive than the BICEP maps. The polarization maps of Planck are dominated at this frequency, at 353, by noise and dust, while the BICEP Keck map are dominated by CMB E-mode polarization. So what are our expectations for dust? In this paper, Planck Intermediate Results, paper number 30 last year, the Planck collaboration studied the spatial and dust spectral distribution of the dust. And so in this panel over here in the left, I'm showing you the B-mode power spectrum of the dust as a function of multiple moments. Let's take a look at the colored dots. These colored dots correspond to measurements at different areas in the sky. So what they saw is that the dust B-mode power spectrum follows approximately a power law when averaging over large sky areas. And they claim no evidence for deviations from this behavior on small sky patches, although the signal to noise is low. They also studied the frequency spectral dependence of the dust, and they showed that the spectral energy distribution of polarized dust emission follows a modified black body model. So this is the model of dust that we used in our analysis. Sorry?
How modified?
It's by a parameter that goes to the minus, it goes with a power of -3. So it's multiplied by a parameter that goes to the power of -3. I'm showing you here a zoom in of the B-mode power spectrum. In this panel, I'm showing you 150 gigahertz crossed 150 gigahertz of the B-mode power spectrum as a function of multiple moment for the combined BICEP Keck map in black, BICEP cross BICEP in blue, and Keck cross Keck in red. In the red line, I'm showing you the lambda CDM expectation with lensing and without tensor modes. And in this plot over here, I'm showing you the cross-correlation between 150 gigahertz of BICEP and Keck cross 353 from Planck. So we can see that the autocorrelation at 150 gigahertz and the cross-correlation between 150 and 353 gigahertz beam modes are detected with high signal-to-noise. And now I will describe the multi-component, multispectral likelihood analysis that we developed for this work. Our fiducial analysis uses single and cross-frequency spectra from BICEP2 Keck data at 150 gigahertz and Planck maps at 217 gigahertz and 353 gigahertz channels. We saw in this analysis that lower frequencies mostly help constrain synchrotron, which we saw has a negligible impact on the constraints on R. For our fiducial model, we took lambda CDM plus gravity waves and a dust signal, and we marginalized over the dust amplitude the spatial and frequency spectral indices. Of course, we made variations to the model and to the data sets, and most of them had very little impact on the results. And so here I'm showing you the results. We can focus on this panel first. I'm showing you the 1D probability distribution function of the tensor to scalar ratio R. And in black, I'm showing you the BICEP Keck combined plus Planck data. Let's focus on this curve. We see from here that there is no significant evidence for a tensor to scalar ratio greater than 0. A 0 to peak range, we can see that this 0 to peak ratio is about 0.4, which happens about 8% of the times in a dust-only models. It is interesting to note also that R equals 0 and R equals 0.1 have approximately equal likelihood. So we cannot say anything about a non-zero detection of the tensor to scalar ratio. I'm showing you here the 1D probability distribution function of the amplitude of the dust, pivoting at L equal 80 and at 353 gigahertz. We can see that we detect dust at a 5.1 sigma significance level. And here I'm showing you a contour plot in 2 dimensions of the amplitude of the dust versus the tensor to scalar ratio. As we can see, they are partially degenerate, and as we expect, less dust implies that we have to have more gravity waves. We made variations to the fiducial data set and model. We added synchrotron component in combination with lower frequency data. We varied the spatial spectral index, the dust frequency spectral index. We extended the band power range from 5 to 9 beams. We varied the lensing amplitude, and we saw that all these variations made little difference on the constraint on R. And this is my last slide. We finally also varied the lensing amplitude. I'm showing you here the lensing amplitude versus the tensor to scalar ratio, and the lensing amplitude versus the dust amplitude over here. We can see that dust and lensing components can be cleanly separated, and we have a detection of the B-mode lensing signal at about 7 sigma. Of course, for this analysis, we extended our fiducial model, our fiducial data from 5 band powers to 9 band powers. So we went up to 330 multiple. So here are the conclusions. The constraint on the tensor to scalar ratio from this joint collaboration is, tells us that the tensor to scalar ratio is less than 0.12 at the 95% confidence level. There is no significant evidence for tensor to scalar ratio greater than 0. Currently, R equals 0 and R equals 0.1 are about the same likelihood. Our multi-component likelihood analysis gave us an uncertainty on R of 3.5 times 10 to the minus 2. And this is a very direct constraint on primordial tensors as opposed to the constraint coming from temperature from Planck. Dust was detected at the high significance. Lensing B-modes were also detected at high significance. The analysis is stable under variations of the data and the model. And many more experiments in the near future will measure CMB B modes. BICEP 3 and Keck at 95 gigahertz, which John will talk about. Planck, SPT pole, polar bear, ACT pole, spider, class, EVEX, ASP, etc., etc. So the limits on R will tighten in the near future. Stay tuned. Yes.
And then you integrate 2 years versus 3 years, but the likelihood growth does not seem to be much narrower for the Keck compared to the BICEP.
I believe, John, correct me if I'm wrong, but I believe the Keck receivers were never, none of the Keck receivers were never as good as the BICEP receiver. That's why the noise didn't come down by a factor of 5.
Keck survey is still much cheaper than the BICEP 2 survey, despite that fact. And so the other reason why the constraints don't shrink very much is that the sample duration is limited at 150 gigahertz. We've already got extremely high signal noise. So if it shrinks those further, well, we'll talk about that.
If you go back on the slide on the probability function,
Yes.
yeah, right there, is that a significant difference between BICEP and Planck versus Keck and Planck?
Yes, I was expecting that question. So we were also worried about this, and we saw, I have here, whoops, this is not, sorry, 1 second. Okay, so what we did here, let's focus on this, we asked this question, and let's focus on this plot. So I'm showing you here the difference of the data, the cross-correlation of the data between BICEP and Planck minus Keck and Planck compared to the pairwise difference in simulations that have a common input SCI. And so because the BICEP and Keck experiments measure approximately in the same patch of the sky, so the signal is approximately the same, but the noise is different. And so when doing this comparison between the difference of the real data and the difference in pairwise simulations, what we found is that the probability to exceed the chi-square is about 0.27. So 27% of the simulations were worse than the data, which is nothing to, it's not optimal, but it's nothing to worry about.
See if this works. Okay, I also want to thank Cora, especially because she just did all of the hard work in setting up this talk, and also it's been a pleasure to have her join our group here and have her be a part of this analysis since last fall. So I just wanted to give you a little bit of perspective on this now that Cora's explained the latest joint analysis. And I couldn't resist starting with this title slide because I got emailed this photo from our own winter rover, Sam Harrison, this morning at 6 a.m. The winter season officially started at South Pole today with the last flight that left. And this is a picture of the BICEP 3 telescope now, taking the place of the BICEP 2 telescope at South Pole. And you can see the enormous vacuum window of BICEP 3, collecting a lot more photons than BICEP 2, the biggest that we could physically fit on this mount, with a mirror that's beam mapping over here, characterizing the beams as we go into the winter season. So that's a preview. There's actually a lot less snow. Okay, so again, I guess all I want to do is start off by putting the joint analysis in some perspective. So the joint analysis with Planck is something that we got underway last summer. The data was actually exchanged in July. The results, as Cora said, are up. They were posted at the end of January and submitted to PRL. They're now provisionally accepted by PRL. You can see the team here working on this analysis. These are about half Planck people and half our side. This was a meeting that we had in November in Minnesota. I actually left from there straight to the South Pole after this. But this is Jean-Luc Pouget, leader of Planck HFI, Ken Ganga, François Boulanger, dust expert in Planck. But here I want to point out our Harvard team that's participated in this. In addition to myself, this is Colin Bischoff, Kate Alexander, Victor Buza. There's Cora, of course. It was a real pleasure working with the Planck team on this and seeing how the teams on both sides came together in this analysis without any prejudice at all, just wanting to use our data together to try to produce the most powerful answer that we could in combination to get at the truth. So jumping right to the results slide that Cora showed, this is in a slightly different format, but exactly the same plots that Cora showed that appear in our paper at figure 6. This is the results of the multi-component analysis that allows us to simultaneously constrain different contributions to the B modes that have different frequency dependence, whether they're coming from R, that is tensors, or CMB lensing, or the amplitude of the dust spectrum or the synchrotron spectrum. Cora explained how we can also marginalize in this analysis over priors for the frequency dependence of these foregrounds, for their spatial spectral indices, for the possibility of correlated dust and synchrotron, for the actual EB ratio, which has been phenomenologically measured now to be close to 2 for dust, which is interesting. All of those things can go in as parameters in this model. This analysis approach is something that we've been working on here at Harvard, especially for the last 12 months, and this was the core of this paper. So it's been developed here by, again, those people I just mentioned, Colin, Victor, Kate, Emmanuel Buder, and now Cora. And so it's been a big effort. I also should say thanks to the ITC and FAS Odyssey Computing for supporting this analysis. All the analysis that went in that paper was run here at Harvard on our supercomputers on Odyssey. Okay, so I promised you a little perspective. Okay, so to imagine applying this multi-component analysis now that we have in January 2015 to the data set that we had in March 2014. So we didn't quite have this framework ready at that time, but we did in the March 2014 release describe analyses of these combinations of data that we had in hand. BICEP 2, extremely deep maps at 150 gigahertz, and then a little bit of frequency information from BICEP 1 at a lower frequency, 100 gigahertz, and from WMAP K at 23 gigahertz to guard against synchrotron. So on those same axes of R and A dust, I guess the first thing that you might notice is that this point here at 0, 0 is strongly excluded. In fact, it's over 5 sigma that we rule out no excess B modes with this data set in March, and that was one of our primary results, the detection of excess B modes. The data combinations themselves only weakly constrain the interpretation, and you can see that by this really strong degeneracy between CMB and dust, much stronger in this data set because we have so little frequency information. Nonetheless, the dust-only model, which would lie along this axis here, is somewhat disfavored by the data, but only at about 1 in 10 odds. And the analysis that we reported in March of last year reached that conclusion, about that 1 in 10 odds, using a slightly different approach. But here you can see it in this likelihood curve here, the black curve. That's the marginalized curve here that peaks at a non-zero R and falls off only weakly towards 0 if you allow the data to freely consider either dust or R as the explanation for the signal. Now, back in March, not being able to say very much about the frequency composition of the signal, just that much, we had the pre-Planck dust models that were in common use, and those offered predictions for the dust level in our field. So we ran all of the models that were publicly available, these 5 here, and they had predictions for this parameter A dust that were in this range 0.2 to 1.2, shown by these horizontal lines here. So these models were all quite uncertain, but nonetheless, the estimates that they offered aligned well with the data. So that's where we were in March, is able to say that much, that these lines of evidence agreed. And then if we take any of these models as a prior and calculate the conditional likelihoods, you get this family of curves here, peaking between R of 0.15 and R of 0.19. And those were the values that we reported as the dust compensated values for R, maximum likelihood values for R, under this range of models, so assuming these models. And that's what we had. So clearly, it was necessary to replace models with data. And as Planck started to do that over the last year, we learned in the Planck dust papers, especially PIP 30 that appeared in September of last year, that the previous models do, in fact, likely underpredict dust power in high galactic latitude regions like ours. So you take the models away, and you're left with these relatively weak constraints. The interpretation is uncertain. So we need better data, and we need the joint analysis. And that takes us up to where we are now, and the results that Cora just described. When we actually finish that joint analysis, which we reported in the last couple of weeks, the results are that degeneracy shrinks quite a bit. The contours, the black contours here, are consistent with the contours before, but they've shrunk around this point here that suggests that dust is definitely detected, and it's at least 40% of the full signal. It's certainly not as high as some of the most pessimistic projections that would have been up off the top of this plot, but it's also not as low as the models suggested. There's no significant evidence in this likelihood for R greater than 0, and we're able to put an upper limit now at 95% that's R of less than 0.12. And as Cora said, R of 0 and R of 0.1 are currently at equal likelihood. So yes, we still need better data, is where we are right now. Fortunately, that's what we do. So this is showing the cumulative sensitivity, so the instantaneous sensitivity in the top panel of our telescopes at South Pole, and the cumulative map depth on the bottom panel of how deep these maps have integrated. The different shades of green show the 150 gigahertz data that we've taken through 2010 to 2012 with BICEP 2, and then 2013, 2012, 2013 with Keck that were folded into that analysis I just showed you. So at the end of 2013, we went down to South Pole and installed 2 new receivers at 95 gigahertz. They took the place of 2 of the 150 gigahertz receivers on Keck. And that map depth is shown here, accumulating over the 2014 season. And you can see by the end of the 2014 season, we've reached a map depth that's equivalent to about 2 seasons of BICEP 2. So it's already extremely deep maps. So let me just show that to you visually now. These maps are in an advanced state of analysis. So this is the BICEP 2 E-mode signal at 150 gigahertz. So remember, the sky for us is dominated by E-mode polarization of the CMB. Flipping to the somewhat deeper Keck maps of the same thing, and adding those 2 maps together, you get this. So extremely high signal noise measurements of CMB polarization. Now, switching to the data we took last year at 95 gigahertz, there's the E-mode pattern. So of course the key is, what are we going to see in the B-mode pattern? And we'll need a proper analysis to do that, and that analysis is what's going to happen over the next few weeks, and hopefully not many months here at Harvard and throughout our collaboration. But to put numbers to these map depths here, if you take those map depths, microkelvin arc minutes say, and you take the inverse square of that to give you the inverse variance at any given point in the map, multiply that by the effective survey area at that maximum depth, you get a total survey weight that are these numbers here in this column. So you can see BICEP 2 was around 100,000, BICEP 2 plus Keck around 250,000. So we're already at 60,000 in these units with the Keck 95 gigahertz data. And Planck at 143 gigahertz, it's interesting to note, across the whole sky accumulates a similar map depth that we got in 1 season with 2 Keck receivers. So it's a remarkably effective way of getting extremely high sensitivity on the sky efficiently with these receivers. Okay, so I'm out of time. So I'm going to have to go quickly through these because I do want to be able to take questions. To show what that will look like now that we have a pretty good estimate of the dust amplitude, we have upper limits on synchrotron, and we have R of 0.05 shown flat in these units of CMB brightness as a function of frequency. This is the extremely high signal-to-noise 150 gigahertz maps we've already made. Adding in, and these are showing the Planck noise levels here. So low signal-to-noise at all frequencies, even at the 353 gigahertz dust map up here. This shows the noise level in the cross spectra that we form between BICEP, Keck, and any one of these given frequencies from Planck. This shows the same thing now, folding in the Keck 95 gigahertz data and the cross spectrum. And it shows how much more power that's going to add to our component separation right at this frequency where it looks like it's going to count. So starting with the data as we have it now, what is this extra constraint going to look like? Well, of course, we don't know how the data will shift as we add in new Keck data at 95 gigahertz. That's why we do the experiment. But if they stay centered where they are, the answers might actually not be all that exciting. We're actually, we're centered at a maximally inconclusive point here in parameter space, if you like. So it's possible that the results will stay just where they are. And then in that case, the upper limits on R will shrink by a bit to 0.10, say. And R equals 0 will still only be disfavored at around 2 sigma. So certainly not something we would call it a detection. More interesting would be, of course, if the results do shift. And if they were to shift to points that are currently at equal likelihood, so at R of 0 or at R of 0.1 in the data right now, this constraining power of this data combination, which we hope to be publishing this spring, could put upper limits on R, in the case of centering around R of 0, at a level of R of 0.056, R of 0.06 or so. And that would be very exciting. That would rule out a lot of compelling models of inflation. Or, if the data starts to shrink around a value up here at the high end, you could start to see evidence for R non-zero at roughly 3 sigma, which would be interesting. Certainly not conclusive yet. So these are both possible outcomes with just the next round of data. Okay, so I've got to go through this really fast now. I can't resist showing BICEP 3 as it was here at Harvard in our lab in October before we shipped it to South Pole. Here is BICEP 3 at South Pole with the Stanford receiver team putting together this giant focal plane, which will equal 4 new 95 Keck, 4 new Keck receivers is what it's effectively going to add to our mapping speed this year. And when we fully populate the focal plane, it will double that again. So we also installed new Keck receivers this year at 220 gigahertz. This is Abby Vireg and Jamie Bach, 2 professors actually working at the same time on a focal plane here, which rarely happens. So both of these telescopes, Keck at 220 and BICEP 3, have achieved first light on the CMB within the last couple of weeks. It's really exciting to us. And so if we ask where we might be with that next round of data, the data that will be coming in through 2015, well, the 95 gigahertz data by the end of this year should equal the depth that we've got now at 150 gigahertz. And the 220 gigahertz data hopefully will far surpass the sensitivity of Planck for tracking the dust. So again, if we have the data winding up centered on either of these 2 points, now we could start to get some really serious constraining power. This would be ruling out a large swath of parameter space if we're setting upper limits. And if we're finding something non-zero, if we're lucky enough to have it peak that high, it could be quite significant. Of course, the most likely outcome might be somewhere in between these extremes. But I would be very happy with either of these outcomes. I think that either one would really move the ball forward and achieve the goals of the experiment. So to summarize, what's coming next? I just talked about these 2 rounds. Spring of this year, the Keck 95 gigahertz will start to add a lot of constraining power where the dust is 5 times lower in power. And by the end of this year, we'll have ultra-deep maps at 95 gigahertz and also at 220 gigahertz. We're also embarking on many more joint analyses as we have these overlapping data sets with experiments like SPT pool. And Cora mentioned a number of other experiments that we're eager to work with. So prospects for what happens next. Well, we have a very successful recipe for achieving sensitivity. And so almost certainly we will be applying it to more sky. So this is a widely distributed map that Planck has made, estimating the dust power across the high galactic southern sky. The northern sky looks similar. This is showing the noise levels on that map. So everything that's in this contour is at a signal noise of around 1. Is really regarded as unexplored territory, but potentially valuable to map out. And getting more sky, finding the lowest dust regions of sky, and if we start to see evidence for non-zero R, making sure we see the same evidence in different regions of sky, are very important reasons for going and getting more sky. Small aperture measurements have been working very well, so expect another round, BICEP 4++, perhaps looking in the north as well as the south. So thanks a lot. So unfortunately, based on Planck, there's still too much uncertainty in these maps. What's being shown here on the same color scale as here is actually the noise, the uncertainty on these measurements of the dust level. And so you can see that these apparently deep regions, these dark blue regions, they're actually just fluctuations. They can't be regarded as significant indications that the dust is really at its minimum here or here. We just don't know until we have higher signal noise data. But we need to explore these regions for sure. But the top priority, the first thing that we have to do is get equal, basically break the degeneracy in the field that we have. We have very deep data at 150 gigahertz. Unequal coverage means that we've got suboptimal ability to do component separation. So once we catch up at 95 and 220, it will be time to get more sky.
What if the next one is clouds?
Yeah, it's a good question. I'm not actually, I'm not sure that they don't. Where would they be? I suspect they would be over here. Okay, so yeah, I guess over here. It's a good question. The most obvious site in the north would be Greenland, Summit Station in Greenland. It's a very high, cold site, and it's dry in the winter months there. Having visited it a couple years ago, I can say the facilities there are about like what we had at South Pole in 1995, so definitely able to support small telescopes like the ones that we've got. And of course, there are plans for making bigger telescopes down there too that people here know very well of. So it's definitely a site that's ripe for exploration. It's definitely a site that's ripe for development. Thanks.
Okay, so thank you for the invite. Normally this is an hour-long presentation. I have a generous 6 minutes to talk about each of two flagships, so I'll jump right in. I'm the project scientist for the James Webb Space Telescope at the Space Telescope Science Institute. I'm also a member of the WFIRST Science Definition Team and the biggest advocate of its Guest Observer program. So I want to just explain where we are with these two programs and hopefully get you guys excited about using them in the near future. So first, at a very basic level, these two flagship missions are natural successors to the Hubble Space Telescope. Hubble has laid this fantastic foundation, and two of the dimensions that we would like to take Hubble in the future is a telescope that has much more power and a telescope that has a much wider area. And that's exactly what WFIRST and JWST do. So let me start with WFIRST, and then I'll conclude with JWST. This is my one-slide summary of the WFIRST science case. This is built on pillars that were identified in the decadal survey and even before. One of those pillars is this survey of dark energy to constrain the nature of dark energy. WFIRST will do this through a multi-tiered survey that includes weak lensing measurements through high precision, high resolution imaging of hundreds of millions of galaxies. It also has a spectroscopic survey through a GRISM that'll look at millions of galaxies for galaxy redshift measurements, and a very impressive IFU to do spectroscopy of supernovae to calibrate the distance ladder. Another one of the pillars shown in the bottom right corner here is to complete the survey of exoplanets around stars, the planetary demographics, by finding planets that are very complementary to the Kepler census, which finds close-in hot planets. The WFIRST microlensing survey is designed to find the colder planets that reside in the outskirts of solar systems. There's also an impressive coronagraph on WFIRST, which is really a technology development program. We've been able to achieve high contrast imaging on ground-based telescopes with coronography and discover self-luminous hot planets. With WFIRST, we're going to extend that capability into space for the first time, and this is a very important milestone if we want to ever image an Earth-like planet around a sun-like star. So what I want to talk about today is the guest observer program. 25% of WFIRST will be unallocated to be peer review competed for you. Right? And so there's a tremendous amount of opportunity here. We've never had a high-resolution, wide-field instrument in space before. WFIRST will be the first one. So there's lots of ways to motivate the science case. Here's two examples that I'll show in my 6 minutes. The Hubble Ultra Deep Field. This is a view of what the universe looks like on large scales. We found 10,000 galaxies in this image. Much of this image tells us how galaxies form, how galaxies evolve over cosmic history, and what the chronology of those galaxies are. But what we realize when we delve into the details of this image is that the most interesting sources are often the rare sources, and we have only few of them. So it's difficult to measure the luminosity function at high redshift for galaxies with the Hubble Ultra Deep Field. And so this is what the Hubble Ultra Deep Field looks like with its 10,000 galaxies relative to a typical WFIRST deep field that people like Pascal will propose to use in the near future. And in a WFIRST deep field, you will measure 1 million galaxies, and so you will completely characterize the high redshift galaxy luminosity function. But even if you ignore that, you shouldn't think of the dark energy survey of WFIRST as a dark energy science program. It's a high-latitude survey where we image 2,000 square degrees of the night sky at Hubble sensitivity and Hubble resolution. We've never had that. We're building a map of the universe at high resolution for the first time. And so this is just what the galaxy luminosity function would look like out of that survey that's being taken, motivated by dark energy science. We're talking about hundreds of thousands of galaxies in the top curve, which is the 5 sigma limit at a redshift of 9. Tens of thousands of galaxies at a redshift of 10. It's going to be absolutely amazing. Opposite end of the spectrum, I work on stellar populations. WFIRST is very exciting for that as well. We show you guys a little movie. Ignore the little horses that are going to come here for a minute. This is for public outreach purposes. This is the panchromatic Hubble Andromeda Treasury program that we're doing with Hubble, where we basically peered into the stellar disk of the Andromeda spiral galaxy and looked at this galaxy as a collection of stars. We're tackling questions like the nature of the initial mass function, how it changes with environment, cluster dissolution, cluster formation, galaxy structure. You're measuring individual stars here at the parsec scale. You can see a dust lane cutting through this image right here. Amazing legacy data set for many relations in stellar astrophysics. So how did we put this together? Well, the ridiculous approach that we use with the Hubble Space Telescope is to target fields in Andromeda hundreds of times to build up a contiguous mosaic so we can see what's happening in this galaxy on large scale. We took 400 separate pointings with the infrared camera on Hubble. This is how you would do it with WFIRST. It would be 2 exposures. Okay? So this is going to be a fantastic telescope. So think about any field in astronomy where you've been limited by statistics. WFIRST might be able to bear on that program. Been pushing really hard to limit the microlensing planet survey and the dark energy survey and make sure that 25% of WFIRST time is unallocated. And so that's the guest observer program. Please take advantage of this in the future. JWST is a completely different beast from WFIRST. WFIRST is a relatively simple telescope with 1 wide field imager and a couple other smaller instruments. JWST is an absolute beast. It's the biggest non-defense research program happening in the country right now. It's going to be the successor of the Hubble Space Telescope. It's going to be at least 100 times more powerful than Hubble if you want to do the same type of science that you've done with Hubble, but it also offers a number of modes of science operation that we've never had in a space-based telescope before. And so we're very exciting, and I think we have a fantastic opportunity as a community to make this telescope one of the most important scientific instruments that we've ever built and use that as a foundation to motivate future bold astrophysics programs. One of the reasons that JWST is very successful is at the time that the decadal survey prioritized the science case, many of the technologies that were needed for JWST to be successful didn't exist. And we've been able to create all of these techniques, all technologies. All 10 of these technologies have now been successfully created, and they're built into the manufacturing of JWST. It's definitely not your grandfather's telescope. JWST is very complicated. It has modes of science operation that we've never used before, like a microshutter array that allows you to do multi-object spectroscopy in dense stellar environments and galactic environments. There are 5 different types of IFU spectroscopy you can do on JWST. There are 6 different types of coronography that you can do on JWST. And of course, you get high resolution, high contrast imaging from 0.6 microns to 28 microns over a huge wavelength range. And you can also track every object in the solar system outside the orbit of Mars. So where are we with JWST? Here's a timeline from today to launch. 2014 was a big year for integration of the science instruments on JWST. This is a module that holds all 4 of the science instruments. It's being dropped, carefully dropped, into a cryo vacuum chamber at the Goddard Space Flight Center. We cool this chamber down to the real observing conditions of the telescope and then test the science instruments. They all checked out fine. Also manufactured the spacecraft last year, began work on that. 2015 is the first time that we take all 18 of the JWST segmented mirrors and put them together, so we make the full 6.5 meter mosaic. All 18 of those mirrors are done, but they've never been put together. 2016 is the first time that on the top side of the telescope, you take the primary mirrors and the scientific instruments and you mate them together and then you test that. On the bottom side, you take the spacecraft and the sun shield that keeps the telescope cool and you mate those and then you test that. 2017, the whole optics of the telescope, including the secondary mirror with the science instruments, will be moved into the biggest thermal vacuum chamber in the world. These are 2 full-grown adults standing at the bottom of the chamber right here. An optical stimulus will shine light on the primary mirror through the secondary mirror down to the instruments, make sure that it works as intended in space. This type of full end-to-end test never happened for Hubble, and we saw what that did. 2018, the top side and the bottom side get connected together at Northrop Grumman, Redondo Beach, California. It gets put onto a barge. It'll go through the Panama Canal to French Guiana and Kourou and launch in October, and that'll be the 4th happiest day of my life. My 3 kids. Okay, so science. So I'm a stellar astronomer. I'm going to talk in my colloquium a little bit about some of the work that we've done in stellar populations. This is a picture of the most massive globular cluster in the Milky Way galaxy. With Hubble and other telescopes, we've been able to study this with imaging and exquisite detail. With JWST, we can peer right into the center of the star cluster, resolve individual stars, and get spectroscopy for hundreds of stars simultaneously. Every one of these little rectangles that you see there is a microshutter that can be controlled electrically, and you can open up any configuration of microshutters that aligns with your astrometry to get spectra for objects simultaneously. The beautiful thing about this image is all of the black that you see. It's not crowded. You're doing spectroscopy at 0.1 arcsecond spatial resolution. Exoplanets. We have a great foundation for exoplanet science. The Kepler Space Telescope, as well as the TESS mission that's soon going to launch, are finding exoplanets. We've learned that exoplanets are just the debris from the star formation process, so they're everywhere. That gives us a great foundation to now follow up these discoveries and figure out what these planets are actually made out of. JWST offers us the first tool to do transit spectroscopy in detail on these exoplanets, so we study the starlight as it passes through the planet's atmosphere. Here's a simulation of a super-Earth observed through JWST for 25 transits, orbiting an M-dwarf. You can detect water vapor, methane, you can detect carbon dioxide in the atmospheres of other worlds. This is absolutely remarkable. 20 years ago, we didn't know if there were exoplanets, and now we're talking about fingerprinting them, figuring out what composition of gases are in their atmospheres. And so this is going to be really exciting, but you need a really powerful telescope in a stable orbit to do this. Final science case is, we've been able to go into this Hubble Ultra Deep Field and actually time tag the different galaxies that are in the Hubble Deep Field. And one of the things that we realize is that as we push the redshift regime and look at the earliest galaxies that formed in this image, those galaxies are not representative of the universe's first galaxies. They appear to be mature systems as opposed to pristine old systems. And knowledge of those first galaxies in the universe is tremendously important in astronomy. They're the seeds of the structure that we see today. It's when the dark matter halos of the galaxies were put together. It's when the heavy metals were created. This is a plot from Pascal showing the star formation rate density of the universe. My basic summary for this plot is we know what the luminosity function of galaxies looks like out to about a redshift of 8. After that, things break down completely. With JWST, we'll completely clean up this range and find those first galaxies at very high redshift. Here's an example of a simulation where I've taken the Hubble deep field, and I'm just going to blink between that deep field and a simulated JWST deep field. All I've done here is extended Pascal's luminosity function of galaxies and shown how the point spread function of JWST is much sharper than Hubble. You pick up a lot of these faint galaxies that you do not detect in the Hubble image, and those are representative of the universe's first galaxies in the simulation. So where are we with JWST? The launch is October 2018. A year before that, which is 2.5 years from now, is going to be the call for proposals. That's when you write programs. Prior to that, we're going to have an early release science program. This is a program to take scientifically interesting data in all of the complex modes of JWST very early in cycle 1 and release it to the community with no proprietary time so you can get your hands dirty with those data sets. Community will shape that program through a call for proposals. Careers to catch on fire in astronomy. Write great proposals on JWST and WFIRST. Yeah, so the baseline model that we're assuming is that Hubble is going to continue into the 2020s, and we're going to have 1 or more years of science overlap with both missions. No, so JWST is an international collaboration between the European Space Agency, the Canadian Space Agency, and NASA. And so JWST will launch on an Ariane 5 rocket, which is a European Space Agency launch vehicle, has a tremendous success rate. WFIRST, there are several launch vehicle options in the U.S., like Falcon 9 Heavy, for example. There are options. And the earliest launch date that we're talking about with WFIRST is 2023, 2024. On that timescale, we'll have very powerful launch vehicles at NASA as well. Okay. Thanks.
Hey.
I haven't seen you in a long time.
I know. I was at Space Telescope for a talk at some point. That was a previous, it was when I only had 1 kid instead of 2, so.
Congratulations.
So yeah.
We'll talk later.
Yeah, I'm not around for very long. All right, so I'm going to talk about a completely different topic than my previous colloquium. So it's convenient that you guys offered to give me 2 chances to speak. So in my few minutes here, I want to talk a little bit about the Dark Energy Survey, its status, and some of the early results. Okay, so I guess I don't have to go into this in too much detail. Obviously, the main science driver of the Dark Energy Survey is what is the cause of the observed cosmic acceleration? Is it dark energy? Could it possibly be that we need to modify general relativity on cosmological scales? If it is dark energy, is it a cosmological constant, or is it evolving in time? What's the dark energy equation of state? So DES is a survey. It's already finished its 2nd season. So this is a survey that's happening now. It's very much a precursor to LSST and WFIRST. So DES is using a brand new, beautiful wide field camera, 570 megapixel camera, 3-degree squared field of view on an existing 4-meter telescope in Chile, the Blanco at CTIO. DES will cover 5,000 square degrees, so 1/8 of the full sky in 5 optical and near IR bands. And it is slated to run for 5 years. So we just finished the 2nd season of the observing, so we have 3 more years to go. In addition to the full sky survey, we have 30 degrees of supernova fields designated for doing transient work that are observed every few days. So repeated observations of a smaller subset of our fields. The DES is a collaboration of around 300 scientists from 28 institutions around the world, so a large collaboration of people working on this survey. I have the Facebook up here. I don't have the blog. There's a wonderful blog actually called Dark Energy Detectives that is gotten a lot of good press, I think, for the layperson and understanding what we're doing. Okay, so this is my one slide science overview for DES. Obviously, this focuses on dark energy, but this is a survey of 1/8 of the sky to much greater depth than Sloan, so there's any number of wonderful scientific things that you can do with this data. On the dark energy side, we're focusing on 4 complementary probes of dark energy. The first one is clusters of galaxies. DES will detect over 100,000 galaxies out to redshifts of around 1. The second is weak lensing shear, third baryon acoustic oscillations, and last but not least, supernova, type 1a supernova in these supernova fields. So the combination of these 4 measures will give us a factor of 3 to 5 improvement in the Dark Energy Task Force figure of merit compared to what we previously have, or what we currently have. So these are the 4 individual methods with the prediction for the combined constraints in red. And the nice thing about these 4 measures, obviously they're independent probes. They have their own systematic effects, so it's nice as a check. In addition, 2 of our measures, the clusters and the weak lensing, are sensitive to the geometry of the universe, but also to the growth of structure, compared to BAO and supernova, which are purely geometric probes. This is nice because the combination of a growth of structure measure and a geometric measure can help you tease out, do we have some possible modification to general relativity compared to truly a dark energy. So the one of these that I'm most involved in is the cluster survey. So measuring the growth of clusters as a function of time. So the number density of clusters, which form as a function of redshift, obviously depend on the balance between gravity, pulling in, and the matter density of the universe, and dark energy, and the expansion rate of the universe. The dark energy here also affects the volume. So here is a simple equation where you have the predicted number density of clusters as a function of mass and redshift. And this is what you actually observe. So in a mass and redshift bin, you count up some number of clusters. Now you're counting up clusters in a redshift bin and in a solid angle on the sky. So you get a volume effect here. The dark energy comes in both through the expansion rate, but also through what actual volume does my patch of the sky that I'm surveying correspond to? So you see a geometric factor here as well. And here's just an example of, for different dark energy equation of state parameters, how the number density of clusters would vary with redshift. And obviously out at the highest redshifts, you're getting the strongest constraints. So the hard part of this is this factor that is put in here. And this is, if there is actually a cluster there, what's the likelihood that in your survey you see it? And what's the relationship between what you're actually observing and what you really want to probe, which is the cluster mass? So in the dark energy survey, obviously we detect clusters as an overdensity of galaxies in space and also color space. And the main proxy we have for cluster mass is cluster richness. So how many galaxies, how many red sequence galaxies are in the cluster? So number of bright galaxies scales with mass of the cluster to some extent, but with a fairly large scatter. So a lot of the work in getting the most out of the DES cluster survey comes in calibrating our cluster masses, and we're doing that with really a combination of probes. Weak lensing from the DES data itself, and I'm involved in some X-ray follow-up of DES clusters, and also we'll have Sunyaev Zeldovich because the DES survey overlaps the complete SPT survey area. Okay, so where are we now? So DES just finished its first 2 seasons of observing. So we have covered pretty much that whole full survey area at about 40% depth. And then the next 3 years, we'll be filling in at greater depth the whole survey. We have early science results based on, and DES performance testing based on some very early science verification data. This was a very small patch of the sky, but done to full survey depth. So we're already testing our performance and getting some early results out of that first science verification data. The message is that DES is performing well. We're achieving the photo-Z precision that we need. Supernova are being detected at the expected rate. We're able to get out weak lensing masses. Our galaxy shape measurements are good, looking good. And just in this first science verification covering about 5% of the survey, we've already identified a sample of 20,000 clusters. And their redshifts and richness estimates also look good so far. So that's basically where we are. These are some of the first, just a survey of the first papers. All of these pretty much come out of that science verification data. We're in the process of doing analyses on year 1 data. Now, the science verification data is too small a field to really do cosmology with, but starting with year 1, we'll have about half of the area at 40% depth, so we can start doing some cosmology with that data. And you can see that the papers so far really run the gamut of, testing our weak lensing masses, photometric redshifts, calibrating the performance of the CCD themselves, but then also a variety of science like the discovery of a superluminous supernova, studies of the outer stellar populations of the LMC, which happens to be in the bottom corner of our survey, and other science results already. Now, I will note that this is what's been published so far. There is a paper release planned for the April APS meeting, so there should be another set of papers on the science verification data coming out in April. And so here's just some fun, pretty pictures to show you what we're getting. So this is just a gallery of some of the clusters discovered just in that small science verification patch, highlighting 2 brand new high redshift clusters in the DES data. Here you can clearly see the clusters as the overdensity of galaxies of similar color and some beautiful strong lenses in there. And just to close, I'm going to leave you with some beautiful pictures of the DES data. So this is a zoom in, a very small zoom in on a cluster in the DES science verification data. So this is just 5 by 3 arc minutes. Zooming out, half an arc minute, 30 arc minutes by 20 arc minutes. Zooming in again, this is most of a single DES field. So just in this one image, there are 50,000 galaxies, and this is just a single pointing. So I will leave you with that. Yes. So in fact, I think the SV data should already be out. The data itself is released on, we've said we'll release it on, I think, a yearly timescale. And then the data products, like the catalog, the galaxy catalogs that come out of the reduction of that data, there'll be two releases, one partway through the survey and then one at the end of the full catalog products. In addition, I should note, DECam is available. So we get the Nights on Blanco from like end of August through February. But the rest of the time that this DES isn't using it, that instrument is available for community time, and there's a community data reduction pipeline available as well. So, yeah. Yeah.
With the result that you expect to have at the end of the 5 years, would it be possible to say something about the evolution of darkness, when you compare with darkness?
Yes. Yeah, that's the major goal. LSST will obviously do that better. You'll be able to look at several time bins instead of one. But yeah, so right now everything is, do I have somewhere here? So this is kind of where we are now. This is an accumulation of Planck and current supernova samples. And you can see that everything's consistent with a cosmological constant, but we really don't have any sensitivity to the time evolution yet. This is the predicted DES overlaid on that, and so you can see our red contours here. So we should have some first constraint on whether or not it's consistent with a cosmological constant, or if there's some evolution. That's really one of the major goals.